All right, here we are with problem number 3 from section 6.2 in statistics, the population of U.S. jails. It says here the average daily jail population in the United States is 706,242. So we're already given one piece of information, and that piece of information is an average. So we can write that off to the side that our mu, our average, is 706,242. We're also given the distribution as normal, and the standard deviation is 52,145. So that's going to be our population standard deviation sigma, 52,145. Find the probability that on a randomly selected day, the jail population is, and for part A, greater than 750,000. So this 750,000 that they gave us, that's our X value. That's the value that we are concerned with. 750,000. We're also given the very important piece of information that the distribution is normal. So that tells us that we can draw a normal distribution. The mean mu always goes in the middle of our normal distribution. And our X value, since X is greater than the mu, we'll put it on the right-hand side. We want the probability that the jail population is greater than 750,000, which means we are looking for the area to the right of our X value, greater than. So what we need to do is we need to translate that into a Z-axis. So when we're looking at Z down here, the mean mu always corresponds to 0. Our X value corresponds to, well, we need to figure that out. So we'll use our formula. Our Z transformation formula, Z equals X minus mu over sigma, and we can substitute in the values that we know. Our X value 750,000, our mean 706,242, over our standard deviation 52,145. Performing our subtraction on top first, we get 43,758. And then dividing gives us 0.839. Now, since we're going to have to go to our Z table for this, and our Z, we need to only use 2 decimal places here. So we check our check digit, which is a 9, the 3rd decimal place, is greater than 5. So we are going to use, for our Z value, 0.84, rounding that up. So that's the value on our Z-axis that corresponds to our X, 0.84. And we can start looking for some areas up on the table. Since our X value is larger than the mean, that means our Z value is positive, and we're going to be using the second page of our Z table with the positive Z values, and we head over to 0.84. So 0.8 is right there, and 0.04, and we look for the intersection of that row and that column. So that there is going to be our area, 0.7995. Now, that area, the area since it comes from the Z table, is always the area to the left of whatever X value we care about, 0.7995. So then our probability, whenever you're dealing with looking for the probability of finding a value greater than your X, is always going to be 1 minus the value from the table. 1 minus 0.7995, and that gives us that our probability P is equal to 0.2005. And that's our answer to part A. Now for part B, we see that we're looking for the probability between 600,000 and 700,000 inmates. So we can draw another distribution here. We have 2 X values this time, so we will be having 2 Z values. Here's our mean mu. Now we can note that both of our X values that we're concerned with are below the mean, so they're both going to go to the left. Let's label them out here. So X1 was 600,000, and X2, we'll call it 700,000. And we can label them X1, X2. It doesn't matter too much where precisely you put them, as long as they're on the same side of the mean, it should be fine. And what we're looking for is the area between them, because we want the probability of getting that the population is between those two values. So we're going to have to do our z transformation twice. We'll have two different z values, actually. Before we do that, we can stick the axis on there. Mu, again, corresponds to 0, and we'll have a z1 and a z2. So z1, we'll use our first x value minus the mean over the standard deviation, 600,000, minus our average was 706,242, all divided by our standard deviation. Subtracting in the numerator gives us negative 106,242, and dividing yields negative 2.037. We'll keep 3 decimal places because we're going to have to round to 2. So our check digit 7 is above 5. So our z1 value that we will use is negative 2.04. So we can go ahead and look that up now. We'll call it P1 will be the area to the left of z value negative 2.04. So now we're on the negative side for the z values. We'll go to the first page of the table, negative 2.0, and we're looking for 0.04. So we trace that down and across, and we get that our first area is 0.0207. So we'll call that P1, and we'll just put that over here. So now we can calculate our second z value by the same method using our second x value. 700,000 minus our average. For the numerator, we get another negative value, 6,242. And dividing that yields negative 0.119. So then for our second z value, since again our check digit's greater than 5, we'll round that up to negative 0.12. So now we can get the second probability, the probability that corresponds to negative 0.12. We go to the table, negative 0.1 and 0.02. And we get 0.4522 for our second area. Now, whenever we're looking for probability between two values, we're always going to just subtract the areas that we got from the two z values, largest minus smallest. In our case, it'll be P2 minus P1, which is the area corresponding to the second z value, 0.4522, minus 0.0207, and that'll give us that the probability is 0.4315. And that's our solution to part B.